Good afternoon, everyone. So for many years now, the Linux community have had all the fun. They've had Docker, they've had great ways of deploying packages, they've had all of this cool technology, and us people running Windows Server haven't had quite so much fun. Well, thankfully, with Windows Server 2016, that's all changing. And this is what the subject of my talk will be about. It's describing what Windows containers are and how you can start implementing them on 2000 Server 16. So my name is Ben Hall. I am the founder of Ocelot Uproar. We spend a lot of time helping companies adopt containers and adopt Docker and how they can potentially improve their architecture with it. We also build our own products internally, one of which is Brown Bag, which is aiming to be like Netflix for developers. So aggregating all of the best conference videos, for example, from here, and representing them in a very nice, easy way to find them. The other is Katacoda. Katacoda is an interactive learning platform for software developers. We basically have a series of step-by-step tutorials combined with interactive browser-based environments, so you can start learning Docker, Kubernetes, Mesosphere, all directly accessible from your browser, all for free. So today, what I want to do is start with an introduction into what Docker and what containers are in the first place. I then want to talk about how that applies to the Windows world and how the changes are being introduced. We'll then look at an example of actually deploying an IIS and ASP.NET application as a Windows container, and then how that actually looks by running it in production and what are the tooling and what support you need in this new world. And then finally, we'll look towards the future and where I see the trend of containers, and especially Windows containers, going. So, as I said at the beginning, containers they're all the rage at the moment. They are the simplest way to get to the top of Hacker News. They're a great way to get retweets when you blog anything. They are what everyone is talking about. But what actually is a container? So if we take a step back and if we look at the physical, real world, every day billions of items are sent all the way around the world in these huge, big metal shipping containers. And these shipping containers have certain key properties. They are a certain size, they're a certain height, and they have the door in a certain location. But most importantly, they have, on every single corner, they have a hook. And this hook allows them to be connected to other containers, and that's how they can build this very strong, coherent unit, which can be put onto shipping containers and sent all the way around the world. But actually what's on the inside and what's inside the container doesn't really matter that much. It could be cards, it could be T-shirts, it could be, most of the time, part-built products. The most important bit is that they are the same spec, the same standard, the same approach. Without that, they wouldn't work. We wouldn't be able to connect them together, and we wouldn't be able to utilize and get the capacity which we have. And software containers have taken the same mentality. Software containers are all based on how do you start them, how do you build them, how do you run them, making sure that they can all connect and communicate with each other. But actually what's on the inside doesn't really matter that much. They could be a Java application and the JVM, they could be a Golang binary, or now they could be a Windows container running IIS. That is not important. What's important is a consistent way to start and build and run. And this is what Docker brings us. So a container starts as an image. The image has got everything which your application needs in order to be able to run. So it's got any runtime dependencies. For example, for a C# application, it will be built and it will be compiled. It will have all the NuGet dependencies which it needs. It will have any configuration. And it will also have the .NET framework and the core CLR if it's one of the new fangled applications. And if it's Java, it will look the same. It will have the JVM set up with whatever particular version it needs. It will have the application jar, and it will have everything to launch. On top of, underneath that is all running on top of Docker, or the Docker engine. Now, the Docker engine is offering kernel virtualization. So if we think back to traditional ways of virtualizing applications and virtual machines, they're all running on top of hypervisors. You have ESX or then managing the communication between your guest operating system and your virtual machine to your underlying host operating system and, as such, the underlying hardware. But this virtualization and the traditional way of doing it also includes a lot of additional overhead. Because your application and your guest operating system need a certain amount of memory, And so you have to pre-allocate a certain amount of RAM. It has also performance impact. Because it's having that translation and because it's being a gateway, it can't maximize the I/O and it can't maximize the CPU usage as it would if it was just running on the raw host operating system itself. This is where Docker is significantly different. Docker is offering kernel virtualization. Basically, it's taking advantage of the kernel from the host operating system and making it available to each and every single container. It's this kernel virtualization which is also offering the protection and the isolation and the security mechanisms. It's restricting what the container can do and what the container can see. Docker is managing that layer. And then below that, we have the host operating system, which you would expect. So Ubuntu, CentOS, Red Hat, Windows Server 2016. And then we have our bare metal server, EC2 machine, whatever we would normally have. And so while you can think of containers like virtual machines, they have got some significant different properties. They have their own process space. So when you go into a container and you ask it what is actually running, it will only say what it actually has been started. So if you're only running a bash prompt, it will just say the only thing running is bash. If you're running a .NET application, it will say the only thing running is this .NET application. Even though the host operating system may have thousands and hundreds of thousands of different processes and different containers, from the container's viewpoint, it's the only thing running on that host itself. Each container has their own network interface, they have their own IP address, and so you can open ports, you can send packets, and you can operate and deal with it and manage it as if it was a physical machine. They have their own root directories, and so if you list all the files on a directory, you'll commonly see things like the user directory, a home directory, a bin directory, everything which you'd expect from an underlying operating system. But this operating system is completely independent from the host. And so you can completely delete everything inside of a container, and the host will be unaffected. And this is because it's completely sandboxed, it's completely isolated and shielded. And so any security is mitigated and protected, and the host is always secure. They also have a lot more benefits than what virtual machines do. So because we've got this kernel virtualization, and because the container is communicating with everything via the kernel, everything is a lot quicker and a lot more performant than what you would expect otherwise. And so we have things like the native CPU performance and native memory, but most importantly, we have native I/O. And so when we're running big tasks, such as running databases or Oracle databases or SQL Server, it's not being impacted by having this virtualization layer, which we traditionally had with virtual machines. Instead, we're getting the maximum performance that the host can offer. And also, we don't have any pre-allocation. Because we don't have this operating system sitting in the way to manage everything, we don't have to pre-allocate that 8 gig of RAM. And as such, we can get much better capacity and much better utilization of the hardware and the servers which we have available. Because the only thing which is actually being used is the memory and is the CPU cycles that the process is running and what the process requires. And as such, we can now start packing our server and actually getting the maximum return on our investment. And when you start a container, all a container is doing is literally just launching the process as if it was running on the host operating system. And as such, everything takes milliseconds to launch. Because the host is already there, the kernel is already ready and waiting, the only thing which needs to start is the process itself. And so everything becomes milliseconds. And as such, you can change how your application works and operates and scales. You can move workloads around a lot quicker and a lot more seamlessly than what you could before, because everything's so much quicker to be operating with. In terms of containers, they have been around for a while. They got created in FreeBSD because the developer of FreeBSD needed to be able to develop future versions of FreeBSD. And so he needed to be able to run them side by side. And this is where the concept was introduced. We then had Solaris and Zones and Jails, which are a very similar kind of concept to containers, just with a slightly different way. In Linux, the LXC functionality was introduced, and Red Hat and Google implemented a lot of additional support in order to make that happen and make that secure and performant. All of this was there, and it had been ready and waiting, and companies have been taking advantage of it for a number of years. But it was actually very difficult in order to be able to build applications on top of these containers. You had to understand the internal workings of Linux networking and bash scripts and the kernel in order to be able to take advantage. And so the barrier to entry was significant. This is why everyone loves Docker. Docker has just removed that barrier to entry. They've made containers accessible and approachable for everyone. And so it's now a very simple process in order to take advantage of all the existing benefits in a very nice, clean, structured way with a great toolset and a great community. But more importantly, it's not the tooling, it's the fact that they've actually got us to agree on something. They've got us to agree on what it means to be a container, how containers are started, how containers are built, what do the images look like, how are they shared, how are they progressed. And if you think back to how the metal shipping containers, if that wasn't a standard, they wouldn't work. And Docker has started to introduce this platform and this standard for people to adopt and build around. And this is why we're seeing a huge ecosystem starting to pop up, because we have this now standardization. Docker itself has got some great tools. So if you go out onto Docker and you download the toolset onto your laptop, you'll get the toolbox. The toolbox is made up of 3 different tools to solve different problems. So the octopus is Docker Compose. This is a way to define multiple containers as a single file definition. And then you can use that definition, you can commit it to your source controller, and then that can launch all of the containers which you need, all of the dependencies such as Redis and MySQL as one single file. You then have Docker Machine, which is the tank and whale. This is for managing your virtual machines on your local laptop. So creating new environments, being able to quickly upgrade them, spin them up, just manage your local dev infrastructure. It's also got hooks into various cloud providers, and so you can tell it to launch an Azure machine or a DigitalOcean droplet, and it will set up Docker and have everything working and configured for you. The other one with Whales plus containers is Swarm. So Swarm is a way to do Docker on multiple different hosts. So manage containers, managing where they're running, ensuring that they're always available, always up, even if you lose a host, and managing the network and the service discovery, and how you can actually start doing it, working with Docker at scale. But Docker is appreciated and respectful that it can't solve every single problem. Even though it does try to, it knows that every company has a slightly different way that they need their network configured, or they have different requirements for their storage drivers, and as such, their mentality is that the batteries are included but removable. If you want to replace how the networking works, that's fine, that the whole ecosystem around it would support it. So you just simply swap it out. And when you launch the container, you just tell it to use a different way of running the network. And then Docker will go, cool, we'll just do that instead. And so this opens up, and this makes it actually easier to adopt and migrate your existing infrastructure over to Docker, because if you have special scenarios, you can actually still start taking advantage of it. So when we have containers, all containers are started based on a Docker image. This image is basically a layered file system and of all of the changes which are required in order to get your application to a certain configuration. And so at the bottom, this is the history of building a Docker image. At the bottom, you'll see certain files are being added. We're doing things like apt-get, app-installed for installing things like Mono in this example. And we're progressively enhancing our base operating system and adding more and more functionality up to the top where we have our .NET application, which was one of the original versions, because it's still using KPM, and that's being installed and that's being deployed. It's this layered file system which has given us a great advantage in terms of reuse. We don't have to keep rebuilding an image from complete scratch per application. Instead, we can have a base layer and a base image which has got, for example, Mono installed, and then all we need to worry about is adding our own application on top of it. And all of our Mono-based dependent applications can reuse this same base image. When we need to roll out security updates, we can do that very simply because we can just change the base image, and all of our applications can get that benefit and get that advantage. And so it makes it very simple to start managing how things are being deployed. Internally, how this actually looks from the application's point of view, the application doesn't see it as a layered file system. Instead, it will just see a normal disk. It will just see it as a normal directory. It doesn't make any differences. Internally, Docker is managing this via storage drivers. And so in your image, if that's been overridden by later versions or later layers, then the application will see that latest version. It's very similar to how Git works and a Git repository will work. Your master and your head will be the latest version, but you can go back and you can move around and you can checkpoint and branch in a very similar way. And in order to launch a container, we simply use the Docker CLI or we use their API, and we do Docker run to tell it to launch a container. In this case, we're saying that we also need access to some ports. So we say open up port 6379 on our host, and that's also what should be communicated with the traffic and a process running inside the container on 6379, and then start the image called Redis. By default, this looks up at the Docker Hub, which is a registry where all of the images are available. It looks for the official one called Redis. If it's not on your local machine, it will download it, and then you have the Redis process running. This is exactly the same process which you would have if you installed it natively, if you downloaded the source, built it, compiled it, and have it running. And so now you can just simply have a Redis process, and it's the same process which you would do for MySQL, Postgres, all of these other applications, just ready, available, so you can just start downloading and running them inside containers. And so just from a very simple development time experience, you don't have to worry about versioning, you don't have to worry about how it gets configured, you don't have to worry about different developers on different machines having slightly different versions, which may become out of sync, which may or may not introduce certain problems. Instead, you can have it all running as a Docker container, every single process and dependency, and everything can be consistent and shared amongst your developers. But there's a lot more advantage than just development time dependencies. Because it's removed a lot of the pain of installing and setting up and actually running the processes, you can start getting much more reuse and taking advantage of work which other people have done for you. So for example, I wanted to do some data science and some data analytics in a very simple way, because I don't understand it. And I wanted to use R, because that seemed like a same choice. But I didn't want to go through the stress and pain of understanding how to set up R on my laptop. And actually, I didn't want to clutching around and hanging around when I didn't even know if I'd be using it in 2 weeks. So instead, I just downloaded it as a container. So there's a R Studio, which is like a R IDE. You run the container. It's got everything set up. It's got R installed. It's got everything configured correctly. And you open up the port, and then you can access it via a web browser. You don't have to worry about how it works internally. You don't have to worry about how to configure it. It's just there, set and ready for you to start playing and start experimenting and start to gain the value which you want in the first place, not how to configure it. So that's how Linux works, and that's how containers have worked for the last 2 years. But what we have now is that Docker doesn't want to be just focused on Linux. Docker wants to allow you to deploy your applications anywhere, be it no matter what operating system, no matter what device. And so it's supported Raspberry Pis and ARM devices and ARM CPUs for the last year. And now with Windows Server 2016, we now have support for Windows Server. So what does that look like? So at the moment, it's currently in Technical Preview 5. I believe it will be out at Ignite in September. I believe there will be another announcement, whether it be an RC or some further updates, further technical previews. But you can go ahead, you can start playing with the technical preview. You can run it on Azure, download the ISI, and start experimenting and running containers today. And what Server 2016 brings is 4 key components, 4 new components. We've got Windows Server Core and Windows Nano. Those are 2 new operating systems for Windows. We then have Windows containers, and we have Windows Hyper-V containers. Significant difference, but operate and work in a very similar way. And how it'll actually look and feel is how Docker runs on Linux. It's got a very consistent, very portable way of how it's adopted and how it's moved to the Windows world. And again, Docker doesn't want you to have to relearn different things or worry about different architectures. They want it to feel transparent, and that's what they've actually done a very good job of doing. And so we'll have our new operating system, Windows Server 2016. We'll have the Windows kernel, which we have already, but with the added benefits of container awareness and container-based features, which we didn't have before. We'll have the Windows version of the Docker engine, which works and looks in a very similar way. And then on top of that, we can run containers. But now we can run containers which are actually running Windows binaries. So things like SQL Server, things like MSNQ, IIS, and ASP.NET applications. taking all of the benefits and all of the advantage which we had in Linux, but bringing them to the Windows world. In terms of Hyper-V containers add an additional layer of security and protection around the container itself. And so by default, containers are secure. They have been locked down, they have additional security, and as I know from Katacoda, people do try and break out, and there have been no reported breakouts in the last 2 years. However, certain companies and certain approaches like PCI compliance kind of add additional restrictions, and so having that shared kernel could potentially introduce some problems. And so this is where Hyper-V containers come in. Hyper-V containers basically add an additional layer of security around the running container itself. This additional layer is a very mini, very lightweight virtual machine. And so when you do docker run launch the Hyper-V container, what it's doing is actually launching a virtual machine, which will give you a different, brand new, isolated Windows kernel. And then on top of that, your container is running. It's all transparent, it's all managed for you under the covers. There's very little overhead. It only adds around 200 milliseconds to boot up. So again, the timing isn't that far off. But we have split the kernel. And so from a security point of view, it's a lot more secure. In terms of use cases, generally for most companies and most problems, Windows containers will solve everything that you need. However, there's two ones which kind of where Hyper-V kind of comes into its own. One is shared hosting. So if you are Azure and you are running potentially malicious code, which is kind of designed to attack the Windows kernel, adding that additional layer and not sharing the same kernel between different clients and different hosts protects everyone else on the system. And so even if they do manage to break out of a container, they'll only get to the virtual machine inside Hyper-V, and they'll have to then break out of Hyper-V, and it becomes a lot more problematic for them. The other one is multi-tenancy. So where you want to have more restrictions and more control over which machines, which tenants can talk to which other tenants. And so this is where the scenarios where you'll be using Hyper-V containers over Windows containers. For the most part, Windows containers will solve the problem. So that's how we've got new features which run containers on Windows. The two new operating systems enable the processes running inside the containers themselves. So Windows Server Core it's kind of like Windows Server. It's got all of the same, or nearly all of the same APIs. It works and feels and looks like Windows. It's got all the things which you'd expect from Windows. So you can remote desktop into it. You have Windows Defender running if you really, really want to for some strange reason. And so it works and operates and handles Windows Server. The benefit of this is if your application is currently running on Windows Server, it should be very easy to port over to Windows Server Core because the APIs and the way it operates and the way it looks is very similar. Windows Nano is the new, very streamlined, very cut-down version of Windows. It has been designed with containers and cloud-based deployments in mind, and that's been Microsoft's focus, especially because they needed something lighter for Azure. And so this is how they came down with Windows Nano. Everything has been stripped down, apart from the very bare essentials. For example, networking, storage drivers, the kernel itself, and a few other bits and pieces like Hyper-V and the core CLR. And so you're talking like it's 1/20th of the size. It's really streamlined. It takes milliseconds to boot up. And as such, this is a foundation for your container image, which you can use to run your own applications. If you think back to if you compare these two new operating systems to Linux, Windows Server Core is like the big proper operating system like a Red Hat or an Ubuntu or CentOS. It's got all of the libraries, all of the APIs, it's got legacy backward compatibility, and it will run pretty much most applications. Windows Nano is kind of like the new cool Alpine Linux. It's been designed with optimization, it's designed to be small, it's designed to be lightweight. And as such, if you're porting applications, you may or may not need to make changes. It will make a best effort, and if you're not doing anything too weird and wonderful, it will probably work. But your migration may vary, especially as you progress to older technologies. And so that's how I see when people are going to be migrating, people will probably start with Windows Server Core, get something working, and then sample and experiment with Windows Nano to see if they can make it more lightweight and more streamlined, and then make changes as and when they need to, when they can. So how do we actually do this? How do we get started, and how do we start using everything? So once you've got Windows Server 2016 set up, there's a new Windows feature called containers, funny enough. So you install that, and that opens up, and that adds all the hooks and all of the APIs which Docker needs to be able to deal with Windows. There are then 2 helper scripts, which you can download, which installs everything, and it will just run and configure the host to have Docker and containers and everything set up, which you need. This script can take a while to run, but it's kind of like, it's not that bad. But it downloads everything you need, it sets up all the services, it downloads Docker, and it also does some really interesting things what I was getting prepared, such as downloading the NSSM, which was like, that's a bit weird. I'd not seen that before, and I was a little bit concerned, like, I want to know what's running. Turns out it's done for the non-sucking service manager, which was like, okay, when you don't want to be dealing with Windows Service Manager, I can understand you want to get something out the door. And so this is the approach which the team took, is like, let's get something working and let's get our feedback instead of making and fixing all of the potential issues which may arise. I have been told that in the future versions it will run a proper Windows Manager, so they won't need this, but it was a nice way that the team are approaching the problem of getting containers working on Windows, is do whatever it takes. And so once you've got containers and once you've got Docker set up, it looks and feels like it's on Linux. It looks and feels it's got the same APIs and everything is consistent. And so when you're dealing with it, it will kind of look and feel like this. You'll have your Docker client, which will be like running on your Mac, Linux, Windows machine, and then that can talk and communicate with Windows hosts or Linux hosts. And then the Docker daemon will talk to the underlying kernel. It will know how to launch processes and how to interact and do everything which you need. Again, from the viewpoint of how the Docker images are structured and how they're layered and how they're built, it's identical. It's the same. They've taken the same experience and adapted it to the Windows foundation or the Windows world. And so we'll have the registry, we'll have our container base image, which is Windows Server Core or Windows Nano, and then on top of that we'll have whatever applications and whatever configuration we need, be it SQL Server or IIS and everything which we need. And then from the containers point of view, when you start it, you do dir on the C drive, and it will have program files, it will have the Windows directory, it will have System32, and it will look and feel like a complete Windows host. And that's because it is. It's just running inside of a container. You may be familiar with the new Windows Linux subsystem. This was introduced in Windows 10, and this is kind of like the cool, you can run bash on Windows. This is completely independent of Windows containers. Windows containers are native. They're running native applications, not a shell kind of like shim layer going on. And so this is all work inside the kernel. And the Windows kernel team have been trying to get this working for a very, very long time. And so it's only recently that they've actually made the breakthroughs what they needed in terms of the research in order to be able to get it in. And I think the advantage of Docker being around has kind of made it jump a few priority lists in Microsoft's schedule. So what is a Windows Docker image, and how do you actually build and run these Docker images? So when you start, after you've installed that lovely script, you will have 2 new Docker images ready and waiting. You'll have Nano Server and you'll have Windows Server Core. With Docker images, everything is immutable. So you won't be running Windows updates, you won't be applying security patches to the running Windows version, which you would actually expect if it was a real virtual machine. Instead, you'll be downloading and pulling the later versions of Windows Server Core, and then you'll be using that as the base for your application and redeploying your new Docker image. And so when we start our container, again, we're using Docker run like we did with Redis. We're saying run our Windows Server Core and start a command prompt. So in the blue, we've got my host running from PowerShell. You can see it's got the install script, which I downloaded. And then inside our container, we do a list, and it's just completely isolated. It looks and feels like a Windows machine, but it's completely separate. Also note that it's running a UI. So in Linux, it's a bit different because of how the display port works. But in Windows, a container can launch UI processes, which will make for interesting future opportunities. So how is this actually being built? So if we start a container, we can start making modifications, and we can start installing things which we need for our application to run. So let's configure and set up IIS. So we can run whatever commands which we normally would run on Windows. For example, ipconfig, we get given back the network card information and the IP address. So it's actually running, and it can do whatever you need it to do. And then we can use whatever features of Windows which we'd normally use in order to be able to configure a box. So for example, install Windows feature web server. So this will install IIS inside of a container. And then that seems to be like a good feature. That's brought our container and our Windows machine up to the level which we require. And so we can exit, go back to our host, and then we can use Docker commit to save that customized container and convert it from a container back into an image. We can then use this image and share it around and promote it from our dev machine to staging to production. We can then also run it. So we can take our newly built IIS Windows container, and we can start it. And so in this case, we give it we're exposing port 80. Instead of with Redis, we expose 6379. We're now running on port 80. We're giving it the name of the image which we just built, in this case, Windows Server Core IIS. And a temporary workaround of we need to tell it something to run in the foreground because it can't do background yet, but that will be fixed soon. We tell it to run CMD. But in the background, that will bring up the container, that will bring up IIS, and so we can access it from a web browser, and we can see the IIS start page, all running inside of a container, which you would expect. However, doing Docker commit is kind of a complete anti-pattern in the Docker world, because it's not repeatable. Right? If you manually going in and touching containers and changing them, the next time you have to upgrade for security fixes, you have to repeat those steps again, and the chances are you will break something or forget something or lose the original script and have to start it all again. So what we actually have is a Docker file. The Docker file is a list of instructions which define what commands need to be run in order to build your Docker image in the first place. And so in this example, I may have an example going forward, we've got a Docker file which says run install feature web server. And then we can use that and we can update that script with everything which we need in order to build our Docker image. But a lot of the time, you don't even need to build an image yourself. A lot of the time, images are already available and already accessible on the Docker Hub. And so there's already a lot for things like SQL Server. It's already been built and already available. Some samples which Microsoft have produced, for example, Redis for the Windows builds, some Windows binaries, MongoDB, MySQL, IIS, which we'd expect, all ready and waiting. So you can just take these images and you can extend them, or you can just run them in your system if you're happy with the defaults. And so again, like with the Linux world, we now have that same features in Windows. And this is an example of the Docker file I was talking about. So we can specify our base image, which originally we did Docker run in order to start it. We now specify that's our starting point. We can give it some nice metadata so we know actually what that container is running and what particular versions. And then we can define whatever commands which we need in order to build that Docker image and bring it up to our spec. In this case, launch PowerShell and add the web server. So, in order to build the image, instead of doing Docker commit, which commits a live running container and turns it into an image, we use Docker build. We give it a nice friendly name, in this case IIS, and we give it a tag, in this case 10. This tag allows us to give it a particular version, and so we can start versioning our different container images, and as we upgrade and we have IIS version 11, we can just roll out that new version and that new tag. And then when we do Docker list, we now have our original images plus the one which we had just newly built based on the instructions in our Docker file. In terms of actually doing this for a real application, we can't just install IIS. We also need to be able to install our own source code. And so the simplest way to do that would be using docker run. And so what we can do is run a command, simply echo hello world to the index.html as part of our build step. And then when we rebuild our application, it will take the IIS, which we had previously built as a foundation. So it assumes the Docker file assumes that IIS has been configured, it's been set up, it's got everything which we need. We build that, and so we now have our IIS base image. We have the customizations which we added for our own application, in this case, creating the index.html. And then we can run that newly created container, again, opening up the port, and then it's accessible from our web browser, which we'd expect. And we've deployed an IIS application running on Windows containers using Docker. And if we wanted to add that additional level of security, i.e. not run it as a Windows container, but run it as a Windows Hyper-V container, we simply specify the isolation level. And we say isolation equals Hyper-V. And so now when we launch that, it will launch that very mini cut-down virtual machine and run our newly built Docker image as a container inside of that virtual machine and not on our host kernel. Yes? So the question was, is this something like boot to Docker? No. So it's something which Microsoft had done, which I'm not internally familiar with, because it's not open source. However, what I believe it is doing is all it's doing is basically the Windows Server kernel. That's what it's booting up, and so it's just a very, very cut down version. And it doesn't even run. It's not running Docker. It's not running any hooks. It's the Windows Server host knows how to use that newly built kernel in order to be able to start the process. And that's what the process is communicating with via. And so, yeah, it's different to the boot to Docker stuff.
You still don't get pre-allocation, right?
You don't, no. So again, you don't, because it's not a proper virtual machine, you don't have to pre-allocate the memory, you don't have to give it 2 gig of RAM. It's just like a proxy for the Windows host kernel. I think that's probably the best way of putting it, using the Hyper-V technology. And also, I was saying, all of these Docker images should be immutable, because we like immutable infrastructure, and we don't like things randomly changing. And so when we wanted to upgrade our image, we wanted to roll out security patches, a new version, we'd reuse the Docker build command, we'd execute the Docker run file, rerun all the commands, and as such, we'd have a newly built image, which we'd then deploy onto our system. And so you'll see things like this. You'll have iOS, and then you'll have the app, and then you'll have 1.1, 1.2, 1.3. And then sometimes people like to label, have multiple different tags for the same image. So in this case, we've got 1.1.3 with a certain image ID, which we've also tagged as latest. And so people, when you want to know what the latest is, you just simply do docker run latest, and then that will pull down whichever particular version is. And so you don't necessarily need to be tracking the version numbers in a different place. You just always say, just always deploy the latest version, and then that will always make sure it will tag, pull down whichever one it's being tagged to. When you start containers, you also have a lot of customizations. You also have a lot of different details and a lot of different options to configure out how your application may be required. And so, for example, you can specify the MAC address of the network interface of the container itself. Useful if you're dealing with licensing, because the license may be attached to the MAC address. And as such, that's how you identify the machine and identify the container. And so you can start customizing that. You can then also customize the ports. So we don't necessarily always want port 80 being mapped to port 80. We can split those. We can have multiple different things running on different ports on our host, but internally they could all be mapped to port 80. Useful for load testing, testing scalability, testing things side by side, and just making sure splitting that container configuration and host configuration. Other things like persistent data is quite important. You don't want the data, which is being saved, for example, from SQL Server or MySQL, living inside the container. Because when you move the container or you upgrade the container, the data will go with it. And as such, you'll lose all the data, which I did, and it's embarrassing, and you don't really want that to happen. So instead, you can specify, when you launch a container, you can specify a volume to map in using the -v. And so you say, point a directory on my host to actually be in a directory inside the container. And so when anything gets wrote to /data, it's actually being written to my host in Docker Elasticsearch. When we launch newly updated containers, we point it back to the same directory, and we can ensure that the data is consistent and available across multiple different independent versions. We can then also start locking it down. So we can start adding additional security restrictions to running processes. And so we can say that, in this example, this certain container is only allowed 20% of the CPU shares, for example. And so we can start adding restrictions and adding additional security and quality of service to ensure that highly available, highly important applications have higher shares than less background running processes. And also ensure that one container can't completely saturate the host. But the fundamental aim of all of this is to simplify deployment, simplify how we can automate the life cycle. So how it actually looks and how everything looks in terms of a pipeline. So we have like our Git repository or a Team Foundation repository. A developer comes along, makes some change, commits into Team Foundation. That will send a webhook, and that will kick off a build task. That build task, instead of just building the binaries like we do at the moment, it will also build and package those binaries as a Docker image. It's then this Docker image which we will promote and upgrade to the various different environments. And we will want to reuse that same image from testing to QA to production, because we want to ensure that we're releasing the same components and the thing which we built is actually what we're releasing and testing and pushing it through. The way we can deal with that and the way we can actually work with Docker, I personally like the Docker CLI because that's what I'm familiar with. But for people who like PowerShell or like to automate and then combine it with large scripts, there is a PowerShell API. I find it a little bit more verbose, but it fits with the PowerShell community, and there's lots of connectlets. So this is connectlet for launching a new container. Again, under the covers, it's using the same API as Docker Run. It just fits and feels more familiar for the Windows admins who like PowerShell. So what's actually happening under the covers and what's going on internally? So the way that Linux containers add the security and add the restrictions is through C groups and namespaces. C groups were created and built by developers at Google, and they limit what a container can, or a process can access and utilize. And so this is where it will say, this one process can only access CPUs 1 to 4. It can only ever maximize 50% of the CPU cycles. It can only ever use 512 of memory. And there's C groups which are making and enforcing those restrictions. Namespaces control what that process can see and what that process can interact with. And so this is how, when I said at the beginning, where you ask a container what it's running, and it says just me, it's because it's in a namespace all by itself. And no other processes belong to that same namespace. The Windows kernel has introduced this, and they've introduced the same concepts and the same principles as what's been in the Linux kernel. And so they will look and feel very similar, even though they're completely independent and completely separate. As I said, the Windows Server team has wanted this for a while. They did Drawbridge, which was like an early prototype. They've done Secure OS operating systems, which have like kind of come and gone. But now it's all available and all in, to the point where this is a Microsoft-led initiative. Microsoft reached out to Docker and said, let's work together on this, and let's make a very consistent standard API, instead of Docker going to Microsoft and going like, we really want this. So it's a Microsoft-led thing, and so that's why I think we'll see a lot of weight being put behind it as 2016 comes out and as it progresses and goes forward. And everything is open source, or large parts of it is open source. The most important part kind of is the shim between how did Docker and how did the Windows Server kernel kind of communicate. And while it's quite interesting Go code and it's quite scary in places, it is all open source. And so you can kind of see how Docker communicates with the shim and how the shim interacts with the Windows kernel. And so if you're inclined and you want to know what's really happening, this is a great place to go on the Microsoft GitHub. In terms of actually building containers, I said that the hub has got lots of images already pre-built. There's also lots of documentation around how you can have certain requirements of features which you need implementing, and Docker files which describe how to run and how to build those particular images. For example, ASP.NET applications, IIS, MySQL, and it's the Docker file with all of the instructions which you need in order to be able to build and deploy what your application requires. In terms of things like doing Nginx, you'll see everything will look and feel very familiar because the Docker file doesn't have that many instructions. It's quite streamlined. And so we'll see things like there's always a from. There's always a base layer of some kind for your Docker image. You'll see kind of like metadata and labels to give it some description. You'll see run commands, which previously we just ran PowerShell install feature web server. This is kind of doing something more complex, but fundamentally it's the same process. And then we can set things like the working directory, so that when we start the container, all future commands always run from that particular directory. And then we can give it like, what is the default command in order to launch this process? So if we don't specify anything, assume that we want to launch the Nginx executable. And so it's all baked into the image. For things like Java, it looks and feels the same. In this case, we're adding, because of licensing and Oracle, you have to go and download certain files from the Oracle website, copy all of them into a certain directory, and then manually, using the add command, add them into the Docker image as it's being built. But it kind of works and feels the same. In terms of actually the Docker image, because Docker is now this cross-platform thing, doing Docker run on Linux should also look and feel the same as if you do it on Windows. And so Docker made certain changes in order to make that possible. So a Docker image now knows how to run itself on different architectures. And so it's got a manifest file, and so when you do Docker pull Redis on Windows, it will download and pull the Microsoft Windows, or the Windows-related binaries, and the Windows-related Docker image. When you do the same command on Linux, it will do the appropriate thing and download the Linux binaries and run those. And when you do it in ARM, it will download the 32-bit concepts. And so when you're moving around and when you're running Docker containers on different architectures and different machines, it will look and feel the same, and Docker will do the right thing. You won't have to worry about prefixing it with Windows or having certain different versions or certain different namings. That will all happen internally and under the covers for you. But what about developers? Right? It's all great having Windows containers on Server 2016, but like, no one's going to be running that on their local laptop, and so what do you actually do? So thankfully, Microsoft have also realized this and have come up with a story. So Windows 10, the insider release, has Windows container support built in. So you can download it from here, download the insider release, and you can get a quick start. Fundamentally, it looks and feels like Windows Server 10, Windows Server 2016. You simply enable a feature, you enable Hyper-V, you download and invoke some particular scripts and executables, and then you have Windows containers running on Windows 10. The way it manages to do this and the way it works is by using that Hyper-V isolation. So it's taking advantage of that isolation level in order to execute and boot a different Windows host kernel. And it just happens that this Windows Server kernel inside the isolation is one which has got Windows container support. And so that's how they've managed to very quickly bootstrap Windows 10 in order to be able to have it to run and build Docker images by using Hyper-V, which makes perfect sense. And now we can just run Docker on our local laptops. We can use that to then build our images, and then we can use that to promote and push it into production, where it will run as Windows containers on Windows Server 2016. And we can just work it and operate in the same way. Visual Studio has additional plugins, and so you can build Docker images from within Visual Studio, add some nice support and add some nice shortcuts, and just make everything feel a little bit more together. So how does this actually look when you're running it in production? How do you actually run containers in production? So for those who may have saw my talk this morning on Kubernetes, Kubernetes is a great way of managing containers at scale across multiple different hosts. It will give you very nice visibility. It will do health checking. It will do self-healing. It will manage auto-scaling. It will have all of these awesome features which you kind of need when you're running containers at particular scale. And it's also got things like it understands how your application works and how it operates. And so when you say deploy this particular thing, it will deploy it onto the most appropriate host depending on what other things are happening in your thing. So you no longer even need to do capacity planning because Kubernetes is doing the capacity planning for you. So that's pretty cool. And that's a pattern called bin packing. And this is what Google do internally. Google match high-running memory requirements or memory applications which require low CPU together on the same machine as high CPU applications which require very low memory. Because they're not constrained and because they're not fighting over the same resources, Google understands how to really maximize the utilization of a box because it's understanding the metrics of the application internally. And this is what will be coming to Kubernetes. Hopefully, one day, we'll all be administering servers like this, and we can actually start flying through and seeing all of them in pretty lights, which would be awesome. Another one which I really like is Mesosphere, DCOS. When you are using Azure, and if you're using the Azure Container Service, this is actually what is powering that. Microsoft have partnered with Azure, partnered with Mesosphere in order to be able to run it. And this has this has also got really cool features, which will probably come to Kubernetes, but host fingerprinting. So when you've got a cluster of different hosts of different types, Mesos will understand which host can run which types of workloads. And so when you execute a Windows container and put it into a cluster of multi-host, it will understand that it can only run it on Windows containers or containers hosts of particular functionality. And so we'll start looking like this, where like a Linux task will only ever run on Linux, for example, whatever is Linux only. With Windows Bash, that's a little bit more blurry now because Windows can run anything. But so Linux-based tasks. And so that will go into Mesos and Marathon, and that will get scheduled onto the Linux-only operating systems. Things like Java, which is portable and cross-language, will be deployed onto any available hosts, whichever has the most resources free. And then things like Windows containers will obviously only be deployed onto hosts which support Windows containers. And so this will be all managed from the viewpoint of the administrators and the developers. They don't care. They just say, run this container. And then Mesos and Marathon will manage which host is the most appropriate, whether it's Windows or Linux. So this is great. And so that's all available now. And we can start running and building Windows containers and shipping applications inside of them. But what about the future? And what does that look like? So Docker will be on IoT devices. There's cool startups like Resin, which will manage deploying Docker images onto ARM-based devices at scale. So they've got really great demos where they've got 3,000 different devices. They do a Docker push, and it pushes to every single image, and you can see it doing a rolling update across IoT devices, or using the Docker API, which is kind of impressive and kind of better than the alternative ways of deploying software onto IoT. SQL Server as a container is now a thing. So why do we have to go through the 10 pages of tick boxes just to install SQL Server when we can just do a Docker pull and Docker run and have a default version of SQL Server running? And we don't have to go through that stress and that pain. But if we're doing that for Windows Server, and Windows 10 now has container functionality, then why can't we do it for Visual Studio? As we saw earlier, Windows containers can launch UIs. They can launch a command prompt. So why can't they launch other applications? So why can't they run Visual Studio? Why do we have to download 2 gigabytes of installation files to spend another 3 hours of them installing and optimizing themselves when Microsoft could do that all for us, ship it as a Docker image, and then we just do Docker run Visual Studio, and everything just works. And you can also run versions independently and side by side, and they won't have versioning conflicts. And when a new version comes out, we just do a Docker pull Visual Studio :2, and it will download and pull the latest version. And again, we can run them side by side. So that's something which I would love to see. And then we start talking about everything as a container, be it our deployed applications, be it our IoT devices, be it our desktop applications. Everything is running and deployed as these Docker images and as these Docker containers. And they can be deployed anywhere. Because everything is independent and it knows what can run where, we ship it into the cloud and it just will run on what is the most available, most appropriate hardware. And it will be deciding that for us. And so we won't have to. We can then focus on more important things like beer. With that in mind, containers and the ecosystem and Docker as a whole, there's lots to learn. It's all very new, and there's lots to try and get your head around. And so to try and help that was one of the motivations why I built Katacoda, is to give you a centralized place where you can go and actually take a step-by-step guide and understand and learn things which you actually need. And so I would love to hear your feedback. I'd love to hear your thoughts. If you have questions, then please do reach out and contact me. With that in mind, we started off by looking at the physical world. We started off looking at what containers are in the physical world and then adapting them and how they apply to the software and how we can have these very consistent ways of building images using Docker build and the API, running them using Docker run, and making it feel and look identical no matter whether it's Redis or IIS. What's on the inside doesn't matter. Windows Server 2016 brings together 4 key components about how containers will operate and how containers will run in production. We've got Windows Server Core and Windows Nano, which are the new operating systems, new base layers to build and deploy our containers from. The containers will then be running from Windows containers, and then if you want that additional security layer, Windows Hyper-V containers. Everything is immutable. So once that container has been built, it doesn't change, it just gets promoted. And then when you need to make an update, for example, security updates or new versions of your app, you'll rebuild that container, again, promote it through, and everything will be automated and scripted for you. And now we have it on Windows 10. We have the same level and the same support for Docker and running containers, what we have on Windows Server 16, available to developers who are needing to build and operate and run these containers and get them ready for production. Next steps, I recommend, obviously, Katacoda. But if you want to play with this, play with it on Azure. It's not very expensive, and it saves you downloading like huge amounts of IIS and Docker images, and it's very quick and very easy to get started with. And then if you want to play with the developer editions and the developer Windows support, download the Windows 10 Insider release, and it will be there ready and waiting for you. With that, thank you very much for your time, and thank you very much.